This research investigates the concept of mobile sensing for structural health monitoring. In a mobile sensor network, each mobile sensing node can be a miniature robot carrying smart wireless sensors. We started exploring mobile sensing through magnet-wheeled robots that climb on steel structures. The robot contains a front car and a back car. Each car has one wireless sensing unit capable of signal digitization, embedded computing, and wireless communication. The four wheels are surrounded by small pieces of magnets providing attraction with steel surface. The robot has infrared sensors for detecting the boundary of underlying structural surface so that the robot moves safely within the boundary. Besides, the robot has Hall effect sensors for measuring and synchronizing the speed of four wheels in real time. The front and back cars are connected by a flexible beam made of thin plastic or spring steel. An accelerometer is mounted at the center of the beam. The video shows a mobile sensor climbing on a steel portal frame. When the mobile sensor reaches its measurement location, the two cars move towards each other so that the flexible beam is bent towards the structural surface, and the accelerometer is attached. After measurement, the two cars move along opposite directions so that the accelerometer is detached. When the mobile sensor reaches the corner, the back car first pushes the front car up, and then the front car pulls the back car up. The mobile sensor performance is first validated by laboratory damage detection experiments. The upper left figure shows an experimental setup. Two mobile sensors navigate on a steel portal frame and take measurements at each location pair. A hammer excitation is applied between every pair of locations. Three damage scenarios are studied. The first scenario contains an additional mass block fixed on the left column. The second scenario has four bolts loosened at the upper left corner of the frame, and the third scenario has a small notch introduced to the left column. Transmissibility function analysis is applied to the data collected by the mobile sensors. Damage is correctly located for each scenario. To further validate the mobile sensor performance, field testing is carried out on a steel pedestrian bridge. A 4-node mobile sensor network is deployed to measure vertical vibrations at the top plane. Commanded by a wireless server next to the bridge, each mobile sensor starts from the inclined member, climbs over the corner, and moves on the top plane of the bridge. One by one, the sensors move to the first configuration. The video shows one sensor navigating on the bridge and attaching the accelerometer onto structural surface for measuring vibrations. Then the four sensors navigate to the second configuration and so on, till they finish the entire bridge span. The structural vibration data are recorded and wirelessly transmitted to the server. The mobile sensor data is shown to have almost no difference when compared with baseline static sensor data. The length of the bridge is about 100 feet. Without stop, it takes each mobile sensor about 5 minutes to travel through. Current onboard batteries can sustain the mobile sensor operation for about 4 hours. We can see that, using a small number of mobile sensors, dense measurement locations can be achieved with very little human effort. Using mobile sensor data, the model characteristics of each configuration are extracted. Then the model analysis for the entire bridge can be assembled through a couple of static reference sensors. The first 5 model frequencies and the vertical mode shapes of the bridge are shown here. Work is underway to develop more agile mobile sensors that can move on more complicated structures. Harnessing latest development in robotics and mechatronics, it is expected that future mobile sensors will provide many new exciting opportunities for structural health monitoring. The researchers would like to acknowledge the support from NSF under the Sensors and Sensing Systems program.